Great. So our last speaker for today is Bingyu Zhang, and we'll hear about capacities from the Chiu-Tamarkin complex.
Okay. First, thanks for the invitation. Okay, today I would like to talk about how to define capacity using the Chiu-Tamarkin complex, which is a microlocal shift theory invariance. Okay, let's start from a short introduction here. In 2006, and Bergin and Potovich proposed some method to study contact embedding, and in particular, they proved the following contact non-sequencing theory. And under the condition, there's a positive integral between the error gaps. And the idea is to compare the contact homology between different contact spores. And then in 2017, and the Chiu proved that this is still true.
Is to respect.
Sorry?
No, sorry, go ahead.
Okay. Chiu proved that this fact is still true. Non-sequence contact non-sequence is still true if we drop the big gap condition. And the idea is to compare what we call the Chiu-Tamarkin complex today, and like it's a shift theory invariant similar to contact homology. And let me remark that this result is also proven by further using a equivalent theory of a contact homology. And today, I would like to discuss. I would like to explain our work in two aspects. And first, we can extend the existence of a Chiu-Tamarkin complex to more open sets, and then we can define some kind of capacities. And second is that we can compute the Chiu-Tamarkin complex of combinatorial domains, and then we can compute the capacity of combinatorial domains here. Okay, now let's go to some detail. First, let's denote the dx times r to be the direct category of shift of vector space over x times r. Please notice that there is an r factor which is important for us to record some numerical information. And then we can define some kind of a shift convolution, which is an imitation of a Euro convolution transform of functions. And then we define the Tamarkin category of x to be the essential image of these convolution functors here. So please notice that the Tamarkin category here, I marked here as one x, but it consists of some shifts in x times r. And because it's an essential image of a triangulate functor, so it is a triangulate category. And now, let's denote the sectional macro support of F in the Tamarkin category in this way. Here, because a sectional means that we forget the macro support of a later T factors. And then for one open set 2 in the cotangent bundle, you can consider two categories. One is a right-hand side, it collects shifts such that it's a micro supported outside of U. And the left side is a category, which is a left orthogonal complement of the right one. And now we see this open set is admissible. These two categories and this pair of inclusion admit adjoint functors which are represented by two convolution functors, such that their kernel P and Q fit into a distinguished triangle here. And a basic property, let's check some basic property here, is that first we can prove that all bounded open sets and all torque domains are admissible. And the second thing is that the functoriality of these kernels, and in particular, we can prove that the pair of kernel PU and QU are unique. And in the compact case, for open set U in the pre-quantized cotangent bundle, you can lift it to a Z equivalent open set U tutor in the one draft bundle of X. And then you can define some kind of a Lagrange microsupport here in the one draft space. And then we can also discuss what is the DU complement and the DU. And then you can study the perspective of open set in pre-quantized cotangent bundle. Okay, now let's fix a positive integral L, and then consider some spaces and sheaves. And first, let's consider the exterior product of this kernel PU of L with alpha entropy, and then we first put it back to this space using a twisted diagonal map, and then you put forward to L and taking sum over R, and then you get this sheaf FL over R. And you can see that FL is the equivalent sheaf, and the equivalent action comes from the cyclic permutation on these different factors here. For the L copies of factors, so you can consider this equivalency. And basically, you can think this sheaf FL as some homology sheaf of a discrete Hamiltonian lobes. Okay, then let's define the Chiu-Tamarkin complex as a equivalent form between stock of a sheaf FL at T to the shifted trivial K model, shifted the trivial K model, G model. And let's see some example here. The first example is the homology of a Chiu-Tamarkin complex of a whole cotangent bundle is equal to the tensor product of this exterior algebra and the homology of X itself. If you like to use a isomorphism, you can see that later will isomorphic to the vertical compact pole homology of the cotangent bundle. And the second example is homology of the ellipsoid in Euclidean space. It's isomorphic to a shifted polynomial ring and tensor with this exterior algebra. And notice that here we require this T parameter, in some sense energy, which is small, not too big. Okay. Maybe basic important property is that if we use the Gemuk-Kashwara-Shapiha shift quantization of Hamiltonian isotropy, we can prove that the Chiu-Tamarkin complex is invariant under compact supported Hamiltonian isotropy of the cotangent bundle for open setting the cotangent bundle and all positive number. And if we take U to be open setting the pre-quantized cotangent bundle here, then we need to restrict that this T parameter equal to the positive integral L. Okay, so maybe I think it's a good time to answer some question. Okay.
So maybe if you could just explain a little more the role of little L here.
L, you mean which one?
CTL, right? The same L that's no, here in the theorem.
You mean the definition, right? Yeah. Okay. Okay. As I said before, that this FL, uh, the stock of this sheaf here, is heuristic. You can think it as some separate between the loop with action smaller than t. This is very I'll copy him to equip it to equip this space with the such that
You've hit the mute button.
sorry.
So you were muted there for a second. Now you're good.
Okay. Sorry. Then the definition of a Chiu-Tamarkin complex that we take the of this merge space.
So there's something a little bit strange going on in which you're getting muted and unmuted very fast. I'm not sure if you're maybe hitting a button accidentally.
Sorry. It's okay now? Okay. Maybe I know what happened. Okay. I think now it's okay. Okay. Now let's discuss how to define the capacities. Now let's fix open set in the cotangent bundle of Rn, and then there is a canonical inclusion here, which induce a morphism of Turner.
Sorry, maybe you didn't answer Sarah's question about what the role of L was, or did he?
You mean T and L?
So just trying to understand the precise content of the theorem you formulated. Could you maybe scroll back to it? Scroll down.
You mean this guy?
Yes, here. So I see the L visually. I just sort of have a hard time understanding. Well, okay, maybe an example for a concrete question is there any relationship between it holding for a certain L and other values of L? Like, is there?
No.
Is it just okay? It's just something about ZL and
and T are some index here. I need to fix them.
Yeah. Okay. And there is like no intuition behind what happens if you try to change the index.
Yes, there are some relation, but it's not quite clear for me now.
Okay. Thank you.
Okay. Thank you. And for this canonic morphism, you can obtain the morphism of F. And then you take stock. You can obtain a morphism here from stock of FL at T to shifted minus D. And this is an element in H0 of the Chiu-Tamarkin complex. Please remark that the homology of L is a right model of this unit algebra because there is K minus D factors. And so one can assume that the capital of K is divided L and L assumes that L is odd. In this case, one can say that the unit algebra A is isomorphic to a polynomial ring tensor with an exterior ring with some degree. And now, for L odd, let PL to be the minimum prime factor of L. And I define the spectrum of U at level K to be positive number T such that there is some L0, such that for most of the final field, this eta TL is divided by U to K. And I define this CK to be the infima of this spectrum. More or less, let me remark that the definition is some kind of imitation of the capacity defined by Good and Hartrin of using atomic covariance symplectic homology. And now I can state, let me state the main result here is that the functions ck defined on all admissible open sets in the sheaf sense satisfy first they are monotone in some sense, and this capacity it is invariant under compact potted Hamiltonian isotopy. But moreover, if U is bounded with restricted contact type boundary, then one can prove that the sectional microsupport of FL is a subset of an action spectrum. And consequently, if the action spectrum is discrete, then one can prove that the CK is represented by some action, and then CK is a conformal. That means that we restrict to the bounded open set with RCT boundary, then CK defines the symplectic capacity here. And similarly, in the contact situation, actually almost the same thing, but because that the invariance of the functions only valid in integer parts, so we have to extrinsic the integer part as a contact invariance, and then we can define the similar F flow, spectral flow as C flow K. And the result is that the monotonicity and the invariance is still true for compact pole countermorphism, but the action selector property doesn't make much sense here. Okay. Now we can discuss something about the collectoric domain. Now for omega open set in positive RD such that omega hat is a reflection of omega is convex. Then we say the corresponding toric domain is a collectoric domain. And then a computational proof for us is that there is a generating function model of a kernel of X omega. And then we can compute the Chiu-Tamarkin complex of a convex toric domain very few combinatorically. And let's fix some notations that omega t circle is some kind of view of omega, and we have some index function here. So the main result here is that if we restrict to a small t, and this convex toric domain is not the whole space, and then we know the minima homology degree of this convex toric domain is minus 2i omega t circle, and as the homology here as a polynomial module of a polynomial ring, it is of rank 2, and its torsion part is pure in negative homology degree. And for each point in the view, there's a decomposition of eta TL, such as in particular one can say that in small t energy, in small t rank, eta TL is non-zero. And let me see a picture here. For example, if I take a convex domain whose view looks like this, and you can decompose it into different pieces of a rectangle here, and more or less our proof actually illustrates that for each integer vertices here, you can find a branch of copy of a branch of the unit algebra, such that they are glued in some positive degree. And as a consequence of the structural theorem here, we can compute that the the capacity of a combinatoric domain is given by this combinatoric formula, and the similar result holds for the C4 of a pre-quantized combinatoric domain here. And then consequently, we see that the capacity here is the same with Chiu-Tamarkin's capacity for a combinatoric domain. And then a bit question related is that is it in general true that our capacity here is the same with Chiu-Tamarkin's one, and or in general action Hofer one when you suitable you collect or in general, and or more generally, in what sense homology of a Chiu-Tamarkin complex is related to the S1 equivalent symplectic homology. And so far we have many evidence. For example, this computation itself is evidence. And we hope to know, and we have more evidence, but now I think I should stop here. Thanks for your attention.
Thank you very much. That's the speaker. Any questions?
Yeah, may I ask a question?
Yeah, please.
So, I guess in this construction of Chiu-Tamarkin complex, you build in Z over LZ action on this complex. Well, and of course you can choose different L. And my question is, do we expect, or is it possible to find some like universal complex so that we can see the ZL action for all different Z, or maybe a different question, like
Yeah.
can we compare
yes,
the different
somehow
L?
I can answer you partially. Okay, let's go back here. Maybe we can. This is also a question of a service question. Okay. Let me see here. Yes, I didn't write before, but we can prove that as a k-vector space, sheaf of k-vector space, we have the isomorphism of FL UK with the F1 UK. So in this sense, we can somehow we are always compute the homology of a later one, but our construction is essentially some way to equip the later one with a cyclic action, and then we can compute the cyclic the equivalent homology. So in this way, I think the later one is a universal one.
I see. Thank you.
And maybe I can say more is that actually in the computation of first domain, we find that actually all action we find are some restriction action of some S1 action. So I very hope that it is some essentially universal one.
Okay, thank you.
Maybe I could make a comment and you will correct me, Bingyu, if I'm wrong. But the idea of the ZL is to approximate S1.
Yeah.
So I think you could also take the sequence of Z over PKZ as K goes to infinity for some prime number. And that should, and in the limit somehow, you should, the only thing you should see is S1, is the S1 action that's underlying. And I think algebraically it corresponds to the fact that if you look at the cohomology of B z over pkz with coefficient in, let's say, in z over pz, for example, then you have two generators as algebras. So you have u, which is of degree 2, which is the one that corresponds to the cohomology of Cp infinity somehow in the limit. And you have an element of degree 1, which is basically, which gets killed when you take this sequence, so which does not survive in a way. And so it seems to me that there's an algebraic way of just seeing the cohomology of doing as if you had an S1 action actually by this algebraic trick. But you will correct me if I'm wrong.
Yeah, I think it's more or less correct, but I don't know how to write how to write down this literally as one action. We only have a
Yes, we only have finite actions that we can, but the underlying object should be the S1 action that you try to approximate with z over pkz, and we go into infinity somehow. Okay.
Yeah, thank you.
Any other questions?
What are other evidences that your capacities are equal to the Hutchings-Good?
Oh, I think I think the action selector is one, right? Action selector is one, and actually, because of functoriality of kernel here, you can see that the Chiu-Tamarkin complex is natural with exact inclusion and of open set. So I believe this is some kind of a Viterbo transform map here. And there's some computational evidence. For example, we can cut off energy in the computation, but depends on some construction of a kernel. So I cannot expand it here.
Okay.
In my paper with Jean-Good, we showed that the capacities of convex toric domains are uniquely determined by some simple axioms.
Yes.
Most important, a kind of representation by a Rabe orbit of a certain Cayley-Sander index. And maybe those axioms determine the capacities for more convex domains, or maybe all of them even.
Yeah, somehow, but maybe for a question for me is that in the shift that we don't have a good index series, so I'm not sure the orbit we recognize by the shift as the correct index with the Cayley-Sander index. That's a problem, so we have to control directly.
I see. It's interesting.
So this is very interesting. I think we should continue the conversation, but let's maybe just thank the speaker again and formally conclude the questions, and then we can keep discussing. So thanks, Bingyu.